In this video, I'm going to be showing you how to find the center of mass of a rod whose density increases as you go down the rod. So this lambda also represents the linear mass density as you go down the rod. So as you go down, it increases in density linearly, proportionally to x. So this is kind of a weird rod. Technically at 0, the rod weighs nothing, but as you go down the rod, it gets more and more heavy, or more and more dense, so at the end it finally has a density of K times L. So this is kind of a weird rod. I'll do another example in another video of a more everyday rod. So you got to use the equation that I showed you in the previous video. Links in the description. Let's see, the center of mass. I got to change the color to white. Okay, the center of mass equation is equal to the integral of x dm divided by big M. Now, the bounds of this integral are going to be from 0 to L, because those are the points that we're evaluating on this rod. So the integral from 0 to L of x dm divided by big M. Now, just for simplicity's sake, I'm just going to multiply both sides by m, because I don't like having to divide by m on every time. So m times x m times the center of mass is going to be equal to the integral from 0 to L of x dm. Now we're faced with a similar problem from the last video. You can't integrate with respect to dm when your integral has positions on its bounds. So we're going to take a look at this linear mass density to sort of resolve this problem. We know that the linear mass density is equal to kx, and we also know that it's equal to big M divided by L. And we also know that it's equal to a little piece of the mass divided by a little piece of the length. And a little piece of the length in this example is going to be dx, because the length is sort of measured in x. So a tiny piece of the length is going to be dx. So we need to find dx in terms of dm, so we're going to multiply both sides by dx. And by both sides, I mean we're going to multiply both sides. We're going to multiply this by dx and that by dx. So we're going to get that dm is equal to kx dx. I use this part right here. And so we have dm in terms of dx, which is good because we needed to replace this dm with a dx in order to have the correct variable of integration. So we have the total mass times the center of mass is equal to the integral from 0 to L times kx squared times dx. Now this is okay because the variable of integration is a position and the integral has positions, so everything's okay. Now this integral is pretty simple. We're going to plot the constant k, and then we have x cubed divided by 3 evaluated from 0 to L, and then we get k L cubed divided by 3. And then we solve for the center of mass, and we get that the center of mass is equal to KL cubed divided by 3m. Now this is technically what it is, but again this is uninterpretable. We have the center of mass in terms of K and in terms of the mass, and basically you can't do this. You'll get points off if you leave it in that. Now the next thing I'm about to do isn't really intuitive at all. You sort of have to follow along and see what I'm getting at. We know that the total mass of this thing is equal to the integral from 0 to L of dm. Now this is sort of an obvious statement, but you see how that's true, right? That the total mass is the sum of all those tiny masses from 0 to L. This statement holds true. What did we say that dm was equal to? What did we say? It's equal to kx dx. So we're going to replace that dm with kx dx. Now we're going to carry out this integral, and we're going to say that's kx squared divided by 2 evaluated from 0 to L. And then we finally got that mass is equal to KL squared divided by 2. Now we have the mass in terms of K and L squared, and we can plug this back in for M. Now if we sub this in for L, and if we sub this in for M, we sort of have to flip this fraction over because this is in the denominator. So we get that K L cubed divided by 3 times 2 divided by K L squared. and we got some canceling. We got this L and those two L's and these two L's cancel. That K and this K cancels, and then we're left with 2/3 L. And that's the answer. Now this one wasn't very intuitive at all. Apparently when a rod increases linearly, you have to place your finger 2/3 of the way down, closer to the more dense part, in order for it to balance. You need to place your finger about right here to balance it. That's a little bit less intuitive than the last one, of course. Now this thing right here, this thing may have confused you. This part, whoops, oh gosh, that may have confused you because like you may have been stuck right here and you didn't know how to proceed to the rest of the problem, and I understand that. I was stuck at this part when I first started learning it too. But what this is you're trying to find M in terms of K and L, and you do that by doing this weird integration, substitution, and whatnot, and you finally get that the mass is equal to K L squared over 2, and then you sub that back in. Just know that if you're finding the center of mass and you have it in terms of weird things like K and then the mass itself, you're usually not done yet. Unless you have very limited information, you're usually going to get a clean answer like this. So I hope that made sense. This is probably going to do it for this video. If you have any suggestions for future videos, leave those in the comments. And if you have any physics problems that you want me to do, either email them to me in the email in the description. And that's going to do it for this video. Thank you.